Hey there, world. Welcome back to the lab. Last week, I alluded to the fact that I was having some difficulty in fabricating my own printed circuit board. The good news is that it can be done. It took me so many attempts with lots of trial and error, but the experience I gained was 100% worth the struggle. I started with no real experience with CNC mills or PCB fabrication in general, so the learning curve was quite steep. I would like to share the process that I have found to work with the Makera PCB desktop CNC. Maybe it will save some of you from making the same mistakes I made. Or you can use these tips to help fine-tune your own fabrication on whatever CNC machine you might have. Maybe some of you have been wanting to try PCB fabrication but don't know where to start. I was in your shoes when I started this project to build a drone for the DARPA Lift Challenge. The best way to become a better engineer, or maker in general, is to jump right in and try things out. So let's get started. Here is the PCB I fabricated using Makera's PCB desktop CNC. I've not added a silkscreen to it yet, and at some point I will, but this board is just for the scaled prototype of my drone. So how do we go from this, a blank copper-clad board, to this, a prototype-ready PCB? Well, there are a lot of steps involved, but as long as you are methodical in your process, it's not as daunting as it sounds. First, you design your PCB using software, and then export the Gerber file so you can use it with whatever CAM software you're using. I used EasyEDA to modify the flight controller designed by Carbon Aeronautics. I wanted to make the PCB slightly larger to conform to the design rules recommended by Makera. Makera recommends the line width and the line spacing to both be greater than 0.2 millimeters. If you use vias, Makera recommends a diameter greater than 0.4 millimeters, and if you are using a silkscreen, the line width should be greater than 0.25 millimeters. Once I had my Gerber file, I went into the Makera CAM software and started setting up the toolpaths to fabricate the PCB. I'm not going to go in depth on using Makera CAM, but if you want to see an in-depth tutorial for using EasyEDA or Makera CAM, leave me a comment and I'll work on it for you. Inside the CAM software, you have to set the dimensions of your stock. Pro tip number 1, don't just go with the defaults. I was using double-sided boards that are 150 by 100 millimeters. At least that's what the website and the package both say. Take a minute and measure your stock. I found that most of my boards were actually 149.5 by 102.1 millimeters, and all of them are slightly different. Why is this important? For double-sided boards, it is extremely important to get this right to properly set up your alignment pins. Otherwise, when you flip over your board, the side of your board will not be flushed with the anchor, and it will become a source of much frustration. After your stock is set up, you can import your Gerber files and set up your toolpaths. I ended up using slightly different toolpaths than what Makera recommends, and I will explain why as we go. The first toolpath I used was a 2D contour to draw the traces and pads on the board. Makera recommends a depth of 0.05 millimeters. I went slightly deeper, setting the depth at 0.065 millimeters so I could sand the copper with 3000 grit sandpaper after the contours were etched, and again after I soldered rivets into the vias. Makera also recommends using a 0.2 millimeter depth when using the solder mask removal tool. I found that a setting between 0.22 millimeters and 0.26 millimeters worked best. I recommend starting with 0.2 millimeters and adjusting from there if you have partially masked pads after executing the toolpath. Then we export the toolpaths and set up the PCB stock for machining. I used double-sided tape to hold the NDF board in place and secured the PCB on top of it using Makera's clamps. Now it's time to etch the top traces and drill the alignment pin holes. Back to pro tip number 1. If our measurements are slightly off, or if the board isn't perfectly square, You will need to do some sanding to the edge of the board on the side that will butt up against the anchor after you flip the board. I used 80 grit sandpaper with a sanding block and checked the alignment pins frequently so I didn't over sand the edge. After your board aligns with the pins and sits flush against the anchor, you can clamp everything back down and etch the bottom traces. Pro tip number 2. Use this step to drill the via holes so you can solder in the rivets prior to the solder mask application. After this toolpath is complete, I soldered the vias using very small 0.3 millimeter rivets. This was a tedious process, but necessary to ensure I had a good connection between the top and the bottom traces on my board. The rivets I used are 2.6 millimeters in length, and the head of the rivet is 0.15 millimeters. What does this tell me? I know that the side of the board with the rivet head will sit perfectly under a 0.2 millimeter solder mask layer. It also tells me that the rivet on the bottom side is a little long. I cut the bottom of the rivet close to the bottom of the board and then used as little solder as possible, while still ensuring a good connection between the rivet, the copper, and the solder. Once all the rivets were soldered into place, I used a small file to file away some of the solder. Be careful when doing this because you do not want to accidentally scrape any copper in the process. I then followed up with some 3000 grit sandpaper on both sides of the board. After cleaning the board one more time with isopropyl alcohol, the board is now ready for the solder mask application. There are a few different ways that people apply solder masks to their PCB, and I tried many of them without much success. Pro tip number 3. Use transparency film and a glass plate to get even and consistent results. I didn't have any transparency film, but I did have document protectors, which also work. I cut one up and cleaned it with an alcohol wipe. The biggest challenge with this step is actually just knowing how much solder mask to apply. This comes with experience. I got way better every time I did it. Once the solder mask is on the board, cover it with the transparency film, and then use the glass plate to spread the solder mask evenly across the board. Once the solder mask is at the desired thickness and evenly distributed, the solder mask is cured under a UV light. Pro tip number 4. Curing time matters. I have 2 different UV lights. A white one that came with the PCB Fabrication kit from Makera, and a black one that I had purchased a while back for a different project. The white one sometimes took over 45 minutes to cure the solder mask, and even then, sometimes the mask would still be tacky to the touch. I found that my other UV light worked much faster. I was curing the boards in 10 to 15 minutes without them being tacky. What I didn't realize at first was that I was curing them for way too long. Let's look at the solder mask removal tool. This amazing tool is a 0.3 millimeter by 30 degree V-bit that is spring-loaded. The spring tension is set so that it cuts through the softer solder mask material, but when the tip hits the harder copper material, the spring causes the V-bit to retract slightly and it will not cut the copper. If you cure the solder mask for too long, the mask becomes hard and causes the spring to retract the bit, thus not allowing the tool to cut through the solder mask. Have you ever tried using this tool and had places where it wasn't cutting through the solder mask at all? This could be your problem as well. I did some testing and found that I could cure my solder mask with my UV light for 3 minutes. That was enough to cure the mask, easily remove the transparency film without the mask sticking to it, and I could remove the mask the way the tool should. Now there will likely be some inconsistencies across your board. The board itself will not be perfectly flat. Your solder mask will not be exactly even across the entire board, and there might be slight variances in curing at different spots. You may have to run the toolpath for several iterations to remove all the solder mask from the pads. I ran 3 iterations at a depth of 0.22 millimeters, and then ran 2 more iterations at a depth of 0.245 millimeters to clear all the pads. Once the top is complete, repeat the solder mask application and removal process for the bottom side of the board. At this point, the hard part is over. Run the tool paths to drill the holes and cut out the board. Clean everything up and wipe the PCB down with some alcohol wipes. PCB fabrication is now complete. I've already tested the PCB for continuity and am ready to solder on the flight controller electronics and get everything wired up for the first mini Vitruvius test flight. Stay tuned because the test flight will be coming out soon. If you enjoyed this video and want to see more, or if you want to stay up to date on the latest developments with the Vitruvius project and the DARPA Lift Challenge, subscribe and hit that like button. Until next time, build, learn, innovate.